All right, people. So today we are going to show an application of Dalton's law of partial pressures in an experiment, right? So this is a very, very good question because it's an application of Dalton's law. I think the previous examples, they're not really practical. They're not as practical as an experiment like this. So let's kind of look at this and kind of see what's going on. So in this experiment, we have potassium chlorate, and it is being heated. So this is the thermal decomposition of KClO3. And what that's going to do is it's going to release some of that oxygen from there. It's going to send it this way through the tube, and we're going to collect it. We're going to collect it, and it's going to come out. And the more gas that comes out, the bigger the volume, right? That's Avogadro's law, the relationship between the volume and the moles. So we're adding more moles. Well, we're adding more volume. But we run into some issues, and the issue is written right there on right above the jar. The issue is that there is water vapor in this container. The oxygen bubbles up, but there is always some vapor on the surface of a liquid. Any liquid, the surface of it, there are particles that break off of it. So imagine the liquid as all these particles kind of just hanging around next to each other, floating around, and some of them eventually get enough kinetic energy to leave off, and those are what create that water vapor. So we have a mixture of gases. So if we know the pressure of that, well, we know the pressure of the mixture, so we got to use Dalton's law to solve this problem, okay? And let's check out what that looks like. So, a sample of solid potassium chlorate was heated in a test tube and decomposed by the following reactions. So, 2 KClO3s break apart to form 2 KCl's and 3 O2s. The oxygen produced was collected by displacement of water. So, that means you just added some gas and it started pushing the water down. And it had a total pressure. So, let's write some stuff down. Let's put P total. Let's just put PT for short. P total is 754 torr. The volume of the gas collected. So the gas collected was O2. So the volume of O2 was 0.650 liters. And it said, and the pressure of the water vapor, the pressure of H2O, is 21 torr. All right. And then they say calculate the partial pressure of O2. So the partial pressure of O2, well, I don't know what that is. Question mark, exclamation mark. All right. And the mass, okay, so calculate the partial pressure and calculate the mass. So we don't know the mass of KClO3. LO3, we don't know that. That comes at the end. So I'm actually gonna I'm gonna write that somewhere over here because I don't want to forget that. Whenever I do longer problems or like two-part answers, I'll always forget. So it always helps me to make a little note off to the side to remember what the overall goal is. It's easy to lose track or lose sight of what's important with problems like these. Now, Dalton's law of partial pressure is very simple. Hello, I had it here. It just disappeared. Whatever. There we go. All right. So, Dalton's law of partial pressure is the total pressure, which we know as 754 torr, is equal to the pressure of all the gases added up. So, the pressure of P1, let's just call that our H2O, right? The pressure of H2O. So, let's say that's 21 torr. And then we don't know the pressure of O2, so we're just going to say PO2. We're going to subtract it. So 754 minus 21. 5 minus 2 is 3. 4 minus 1 is also 3. So we got 733 torr is equal to the pressure of O2. All right, but we have the pressure. We have the pressure of O2, and it seems like we're done. Yay! But we're not done because we need the mass of KCl3. How can we go from pressure of O2 to grams of KClO3? Well, there's this equation called the ideal gas law. I'm sure you've heard of it. That's PV is equal to nRT. We know the pressure of the O2, we know the volume of the O2, we know what R is, and do we know the temperature? Let's check it out. It says 22 degrees Celsius. So the temperature is 22 degrees Celsius plus 273. Why do I need a calculator? 295 K. All right, so let's rearrange this formula, because if we want to find mass, what we're looking for is moles. So we need moles of O2, so then we can go to moles of KClO3. So let's rearrange this formula so that we solve for, and oh, what the heck is this? Did I have a formula written out around here? I thought I did. Oh well. So let's divide by RT to both sides. Let's divide by RT to both sides to get the equation like that. And let's write O2 here so that we don't lose track. The moles of O2 is what we're looking for. So let's plug this in. And I'm going to get rid of this because we've already done it. Move away. I don't need you. All right. We don't need the P total. We'll just scooch this up over here. All right. So the moles of O2 we don't know, but the pressure of O2 was 733 torr. The volume of O2, I have it right here. And then I'm going to put parentheses. And then underneath will our R value. Do you know how lazy I am? I'm going to go and find an R value. R, where are you? Yeah, look at that. You can't do this. You're jealous, huh? You got to write by hand, peasant. Sorry. Yeah, I got to use a mouse, so you're lucky. You got the appropriate tools. You'll probably finish way before me. And now the temperature was 295. 295. K for Kelvin. I knew this guy named Kelvin. That's a cool name. Kelvin, Lord Kelvin, the guy, I'll talk about that later. His name wasn't even Kelvin. He was like some, I think some French dude. He got killed. Wait, no, I'm thinking Lavoisier. Got his head chopped off. French Revolution. For being rich, he was it was very, very sad death. Very young person. And let me double check that my math is in fact correct. I do not think so. I do not think so. Something seems off. Something seems off. Something seems off. Yes, I know what's off. I know what's off. What is off? Look at this. Always write your units because your units will point out your mistakes. You got torr, we got ATM here. No, Mr. Sanchez, you're making a big old mistake. So, units save lives. Look, liters cancel the K cancel out. We need something to cancel out the torr. So that the only thing left is moles. So what we're gonna do is like off to the side, we're gonna convert this torr to ATM. So let's just do that right here, just off to the side. So 733 torr. To turn that into ATM must go at the top, and at the bottom, well, ATM is the same thing as 760 torr. The torrs cancel out. And now we get 733 divided by 760, remember, because it's at the bottom, 0.964 ATM. And let's go and plug that in right here. Uh-oh, that looks like a 9. I don't want to mess that up because when I put in my calculator, I'll cry if it's wrong. All right, so look at that. The ATMs now cancel. We're dividing by 1 over moles, which our answer is just going to be in moles. And let's check out. We got 0.964 times 0.650 divided by 0.08206 divided by 295, and we get 0.025, and there was 3.66259 moles of moles of O2. So we're done. Yay! On to the next video. Except, good thing I have this right now because I did almost forget. We need to find KClO3. So a little bit of an issue. Now that we have moles, I'm gonna get rid of all this other junk. Okay. I'm gonna get rid of you. Leave, please. Uh-oh, I copied you. I didn't want... Stop bringing your friends. Yes. Alright. So we found moles of O2. But we need moles of KClO3. So how do we go from moles of O2 to moles of KClO3? You guys are probably familiar with it. It's called the mole ratio. The mole ratio. So where do we get that? Balanced chemical equation. So there's 2 KClO3s for every 3 O2s. So we put 3 O2s and then a 2 up here. Now that's going to give us moles of KClO3, but we want grams. And we know that 1 mole of KClO3 is equal to its molar mass. And I like to plan ahead. So I found this. And I copied and pasted. I looked it up because I get tired of asking asking Siri for things. And this is grams of KClO3. All right. And let's check it out. Our setup seems to be correct. Look, the moles of O2 will cancel with moles of O2. The moles of KClO3 will cancel with the moles of KClO3. Only thing left is going to be grams of KClO3. Let's do a little bit of quick maths, and then we're done with this video, and you'll have like 36 of these problems left to do. Multiply 0.0259 times 2 divided by 3, multiplied by 122.6, and boom, we get 2.12 grams of KClO3. And then I'm going to box this answer so it looks all pretty. And then that's it, people. This is how... it just kind of looks like stoichiometry, but in reality, this problem would not have been possible without an understanding of Dalton's law of partial pressures. If we didn't know it was a mixture, the mass would have always been wrong. If we didn't consider this as a mixture, it would have been off by a certain percentage because the water pressure changed things. So that's just kind of it right there. I don't think I got another. All right. Next video, we're going to be talking about the kinetic molecular theory, conceptual wise. No more math for this one specific section. I'll see you later.